I'm going to give you a non-scientific view of what we, as people who build robot hands and are trying to use them, are looking at and for in tactile sensing, and what we see the challenges are in that. If you saw my talk in Taros, now is the time to go and get a coffee, because this is not going to be substantially different to that one. So firstly, a bit about Shadow. We've been building robots since the 1980s as a group of people interested in doing that. We set up a company in '97. We think we're the longest running robot company in the UK. No one seems to contradict us when we say that, so we're going with it. We've been building primarily robot hands, although we've done all sorts of other bits of robotic technology over the years. We sell them all over the world to people looking at doing R&D in robotics primarily. We work with people all over, from West Coast US through to China and Japan, mostly Northern Hemisphere, not quite sure why that is, just a kind of statistical anomaly. And we're very big on doing collaboration. So one thing we really like doing is finding a problem, finding someone else who's good at that problem, and building some kind of collaborative project with them to address that problem on the space that we're interested in. So we work with kind of all sorts of interesting people all over the world, from space agencies through to airlines, some of the big research organizations. If you saw last year, the year before, OpenAI's recent work about turning Rubik's cubes, or cubes in their hands, that was our robot hand they were using for doing that. And we're working with them on improving the hardware to make it easier to do deep learning with robots, because if you've ever tried doing deep learning with robots, you'll know that the first thing deep learning systems tend to do with robots is to smash them. For a robot manufacturer, that's great, but it's not so good for a researcher, because frankly a smashed robot is not that good for doing any further research with. So making robots more robust has been a kind of interesting outshoot from doing that. Those numbers are out of date. That's what we were doing 2 years ago. I think we're only running 3 Innovate UK projects, but we're in 4 Horizon 2020 projects. We do a lot of collaboration, and one of the reasons we have a Spanish office, a Spanish company, is to continue to do that collaboration after the end of October. Thank you, government. It's not one of the more fun bits of the talk, but it's something we as a business have to address. We're trying to work out what to do with robot hands. That might sound like a really silly question, but there are obvious places where you think you should be able to deploy robot hands to do tasks, and yet people are not doing it. So the goal for us as a business is moving from research to innovation. And there's an old saw that research is defined as taking money and burning it to produce ideas. Innovation is defined as taking ideas and turning them back into money so you can do more research. So we're trying to work out how to take the ideas and turn them back into money by applying them. And understanding why people do and don't want to use robot hands for things, when you look at the problem and say, but obviously you want to put a robot hand in there, and they say, obviously, and yet we haven't, and why haven't they? So that's kind of at the commercial end, those are the problems we tend to worry about more than the scientific challenges of how exactly do we understand a sensor, understand contact, understand force. But we also have to worry about those. So this is, as I say, the work OpenAI we're doing. You can see there, they've done some really, really impressive stuff. When we first started building robot hands back in 1997, 8, we thought it would be relatively easy to program them. How wrong we were. It turned out that actually building the hardware was only one of the really big problems. Once we'd done that, we then found lots of people said, oh great, now we can work out how to program them. And we checked the literature, and indeed no one knew how to program robot hands. So this kind of work is really, really impressive, because it is a method of programming a robot hand. It's not closed in an analytic sense. No one actually understands how to do that task. They've simply built a system that can search until it can find a mechanism for doing it. So it's very much the idiot savant approach to solving a problem. Try anything, if something works, capture it and do it again, as opposed to an actual scientific hypothesis. Here is an algorithm that will work. We have tested it and shown it does. So what we've been doing with this, I said we've been looking at where we can apply robot hands, and we came to the general conclusion that the most interesting space was putting them in places where humans don't like to be. Tactile sensing is necessary for that, because when you put a robot in a remote location, you want to understand what it's doing, what it's interacting with, what's going on. So this is some work we've been doing in the last year. This is a fairly complex system. It's using the SynTouch BioTacs for several of their sensing modes, and it's using BioTacs partly because we're great friends with Jeremy Fischel there from SynTouch, many of whose slides I've cribbed for this talk, and partly because the BioTac actually is one of the best sensors at replicating the way the human sense of touch works. Because human touch isn't a single sensing method, it's multiple different methods embedded in the finger, and we seem to use all of them. And it doesn't just depend on touch, it depends on sound, and it links in with vision, and there are all kinds of interesting results where if you can hear things, your sense of touch improves. What? That doesn't make any sense, it's a sense of touch. But actually our brain just adds touch and hearing together and uses them as a combined sensing method. And you can see here we've got something, on the left is that's the second time we ever tried doing that. The first time we tried doing it was from California to London, and instead of hello he managed to type help, which seemed like a good starting point. But you can actually just about understand what that you are typing and feel the sense of touch there. And obviously the physical human interaction there is something. We wouldn't do that with something that wasn't a cobot, let's put it like that. But we are taking advantage of the fact that we have the sense of touch to actually tell how and where we're touching Luke on the shoulder there. So just to kind of walk through this is cup stacking. It's one of those simple yet really exciting demos when you do it in front of people, because no one quite believes that you can actually stack plastic cups with a robot until they see it done, and then they're like, go on, do it taller, do it taller. It takes about 5 seconds for the excitement to wear away and people just challenge you. But Mike there, this is probably after he spent 6 or 7 hours playing with this system, and he can reliably stack cups about 3 or 4 times slower than he can doing it directly with his hand. So that's a kind of interesting result in itself, that using this system is within an order of magnitude of doing the task directly. It's still not as fast as doing it directly, but because of the sense of touch and because of the visual acuity he's got there, he can do this task pretty much comparably fast as he do it normally. How is the system made up? Well, we have the haptics gloves. So you were asking about tactile feedback, how you render back to the person. Haptics have spent a lot of time and effort working out methods to do that, and their glove does this rather well. It has a rendering array on each fingertip, which is pneumatic. I think there are 12 pneumatic elements there, which are driven by high frequency valves. The primary limit on that is the fact that the valves are 1.5 meters away from their fingertips, but the sensation, the response there is really, really good. There's also palm sensing, or palm feedback elements, resistive stiffening elements, and fingertip location tracking and wrist location tracking. So that gives you a really good way to capture the human hand movement and turn that into something that can be rendered into the robot, and to take data back from the robot or from a virtual space, and render that back to the human. Then the actuation component of that is the shadow hands, 20 degrees of freedom, 24 movements, 20 motors, 40 strain gauges, 24 position sensors, a few other bits and pieces. Fairly complex piece of kit. And the BioTac we're using there, along with vision, hearing, to get the sense of what's happening in the world and render it back. But what we're doing here is we're not trying to program a robot. We're closing a loop between the human and the world in such a way that the human can do the hard part of the task, because we still don't know how to program robots to do hard tasks like this. So what do we get from tactile sensing? This is not my field, so I am winging it a bit with someone else's slides here, so apologies to those of you who actually know this material far better than me. But we know we have multiple different types of data coming from the fingertip. We have force and deformation, we have temperature, and we detect temperature in 2 different ways. We detect heat and we detect cold. We have vibration sensing, with pain. We have position and velocity measuring in the fingers, and we have the force that we have some sense of how much force we're trying to exert in the muscles. So there's a real range of data there, and understanding which of those we have in a robot or which of those we need in a robot is pretty much still a big open question. Our approach therefore is to say put it all in and see what we can do with it. If we can't do something and we have all the sensing, then it's not because we're missing sensing. The sensing might not be good enough, but at least it's there. Once we can do the tasks, then we can work out which sensing we actually need. The other challenge with this is that actually most of those sensing modalities are pretty hard to implement. We do position and velocity well in robotics. We're very, very good at measuring motor outputs. We're very good at putting encoders on joints. We're very good at tracking movement. We're pretty good with strain gauges. We can put sensing on tendons. But when it comes to vibrations, thermal sensing, force and deformation on the fingers, actually, as we've seen earlier, there are lots and lots of options, but there are no canonically right answers. If I say to myself, I want to sense this well on this fingertip now, there isn't a good spec for how to pick and choose those sensors, in the same way that if I say I want to measure forces from 1 to 10 newtons with a resolution of this, specing my strain gauge is going to be pretty easy. Or if I say I want to measure angle at a resolution of 0.01 degrees on a rotation joint of 10 millimeters in diameter, getting an encoder for that is going to be a fairly standard problem. Tactile sensing still is hard to do. The BioTac's nice because it does provide a lot of information. It's got this electrode array inside it. It uses a deformation of the fluid and the deformation of the electrode array to give you information about contact location. The pressure sensing is in there through the little tube you can see there, goes to a little hydrophone over there. It does temperature sensing as well. And you can get quite a lot of information out of that on single points of contact. When you start getting multiple points of contact, not so good, gets confused easily, but most of the time you're trying to touch, well, at the moment we're still trying to touch one thing in one place and having trouble doing that, so multiple points of contact is something we don't yet need. The vibration sensing is nice because, coupled with the fingertip texturing on it, that gives you lots of information about the quality and the nature of a surface you're touching. And that's very important because actually a lot of what we do with objects is to understand them through the feel as we move across them, rather than just a static contact. There's a whole host of references here to the SynTouch work on this, which is very, very solid work, which I completely don't understand. So please don't ask me too many technical questions about that. I can tell you why we like them, but I can't tell you why the physiology of this actually works. We'll talk about temperature sensing briefly. One of the nice things about that is that you can actually detect what material it is by the thermal conductivity properties. You can tell that heat is leaving the object and how fast, leaving the sensor and how fast, and that gives you an interesting insight into what the material is and what temperature the material is already. And SynTouch has done some really nice work characterizing a set of effectively feature vectors of their sensor that lets them characterize objects and do surface texture discrimination, surface understanding, which is great, but I can't use that information yet, because I don't have a good way to propagate that information back to the human. And this is back to the tactile rendering problem. How do you show the human the data that you've captured from the robot? You interpreted it, you've understood it, but what do? Do you put something up on a screen to tell the person? Do you give them an audible indication? Do you give them a sense of some kind of contact on their arm or their back? And one of the challenges here is that nobody really knows. We have had so little time on robots that have really good tactile sensing that the whole question of how do we do tactile rendering well is basically, again, even more of an unknown than how do we spec our sensors in the first place. So this for us is a really interesting challenge, is we've got the data, how do we make use of that so that a human can interpret it? We can interpret it with machine learning, we just can't do anything with it when we've done that, but we can't yet get it back to a human. So, as we all know, touch is really, really important for interfacing with the world, for understanding the world, for doing things. It is one of our primary sensors. Operating with touch but no vision is a lot easier than operating with vision and no touch. There are some really nice pieces of research on what happens when you try and operate with vision and not a sense of touch. You crush things. It's really, really common for robots to crush things. Our general perception of robots as big, strong things is because they don't have the sense of touch, the sense of feedback to stop them doing that. Meanwhile, if you've got someone who's an amputee and there's a person using a prosthetic arm, it's really, really hard for them to pick up objects without a sense of touch. But they can do it. But if you look, they're absolutely focused on doing it. The person's attention is completely on the problem of how do I touch and pick up and hold the object because I can't feel it. There's some really interesting research into how dexterous humans are and how we can make robots that are more dexterous. As you can see there, the bottom right-hand side, the human can do the task in 4.5 seconds, the robot can do it in 0.4 of a second. But that's a very dedicated robot. That's a special purpose machine built for exactly one task. If we change the task slightly, the human would still be able to do it. The robot would fail completely if the cube was 20% bigger or 20% smaller. It just doesn't have the adaptive capability, whereas a human does. So that's a kind of really interesting point for us, is that a sense of touch is necessary not just to be able to do tasks, but to be able to adapt to slight variations in tasks, to changes in tasks, to understanding an object when it's occluded or different to what you're expecting. So we're looking at what we can do with this in industry, and there's an old joke that if you don't know what you're doing in robotics, you say, well, it can obviously be used for disaster recovery. Because no one can really contradict that. Pretty much anything is a good idea in a disaster situation. Anything is better than sending humans in. There are other areas where sending humans in is still the thing we do and we would prefer not to do. The picture down there is a piece of work in nuclear decommissioning. If you're not familiar with that as an operating environment, and you don't need to be probably unless you happen to be really interested in it, the person on the left is wearing what's called an air-fed suit. So they're completely bagged in plastic. Their air comes in, there is very, very poor ventilation, very poor circulation. The health and safety executive recommends you do not wear one of these for more than 3 hours a day because you will collapse through dehydration. You actually sweat continuously while you're in them, and the sweat has nowhere to go. So at the end of 2 to 3 hours doing a fairly heavy manual task there, that person will be standing in basically sweat up to there in their boots, and the first thing they do when they get out of that rig will be to sit and just hydrate continuously for 10-15 minutes just to get their body back to a normal temperature and a normal state of sort of fluid levels. Meanwhile, the task that they're doing in there is in a highly risky environment. It's an environment heavily contaminated with dust that's radioactive. There's risk from sharp objects, from dangerous objects in there. If they were to cut their suit, they could become contaminated by it. If they had an actual accident involving a piece of tooling, the injury is exaggerated massively by the fact that the area is contaminated with effectively radioactive dust. So that's not a nice job. At the moment in the UK, to do one site in the northwest, they think they will have to do that 1 million times. That's a lot of people putting on plastic suits with air hoses and going into dangerous areas and trying to focus and concentrate on doing a difficult task in what are basically horrific ergonomic conditions. That 1 million times is probably a lowball estimate because every so often that estimate creeps up a bit and creeps up a bit. If you're a UK taxpayer, you might like to know that we're committed to spending between 1 and 300 billion pounds on that problem. That's money that the UK will spend on that. So if we can get that cost down by any fraction, that's a lot of money to spend on something else. Pretty much anything else, frankly, or not spend it at all. But this is a big problem and it's worth addressing. And this is a really good example of a problem where effectively robotics should be being used, but it barely is at the moment. Because it's very hard to make robots with comparable dexterity as a human, and it's very hard to give the human controlling them a sense of immersion into that. So what we've been trying to do is effectively to crack that problem, to say how do we put a sense of touch into a different place so a human skill can be transported into another location and the human can do a task there in such a way that they feel confident and comfortable to do it, and so does their manager, and so does their manager. Because actually that's often the bigger problem, is not how do we do the task, it's how do you convince all the people up the chain that the task is being done reliably, safely and efficiently. And what that often comes down to is just simple confidence in we've seen it done, we know how it's done, we've tried the system, we all understand what's happening, we can feel it's right. And it's really interesting that a sense of confidence is built in these cases by people saying, yeah, we feel that that's the right approach, we feel that that system is safe, we feel that. So the sense of touch has become embedded in our language and the way we think about things because it's so important to us. There are obviously other things you can do once you start being able to put robots in complicated places instead of humans. You can scale the number of robots you have by having people controlling many robots. You can quickly get skills places. So if you've ever owned a large expensive piece of machinery and equipment, you'll know that there's always a point sometime in the year when someone comes along and says, yeah, we can't use the tooling today. Why not? We're waiting for the repair guy. Where are they? Germany. When are they going to be here? Tuesday? Can they get here any quicker? No. So we're just going to have to not use this piece of machinery for 10 days because the person who can fix it is in a different country. Yes. Okay, well we're stuck. We can't do anything about that. Why can't that person connect to the internet and through to some robot I have in my office and be able to fix the machine? Because all we can do is hold a camera up to it at the moment and they can kind of see what's going on, but they can't really take it apart, and they need to hear it, and they need to feel it, and they need to plug and unplug things. So there's really interesting approaches where once you start to have robots with a sense of touch in other places, you can then change the way we think about doing tasks at a distance, change the way we think about moving skills around. There are tele-robots and robot systems that work to do tasks remotely at the moment. The Da Vinci surgical system is actually a really good example of doing a task remotely. The surgeon is not in the place anymore, they are just off to one side. Remote does not have to mean a long way. Remote just means not actually doing it. It gets better if you can do it with touch, obviously, I would think so, but it can still be done without it. So it's an important point that we don't need touch, we just like to have touch. The nice thing about this is when you get it right, it's so easy to use that any billionaire can pick it up and use it in a matter of seconds. The training time for doing that consisted of us saying, please don't try and grab something if you drop it, because if you grab something when you drop it, you will probably smash the robot into the table. And that's it. That's the entire training process. So it really is a system that you can now put on and just wear and use. And I have to say that if you ever get the opportunity to have him use some of your hardware, it's great PR, fantastic PR. For some reason, everyone seems to really, really like the idea. So we've been looking at decommissioning as a problem. I mentioned some of the details of that to you there. The cost, these are some of the low-end numbers. That UK number is very definitely the polite external consumption number rather than the one civil servants tell you late at night, but it is a big problem, and it's a long-term problem. It's a 100-year goal to decommission the UK. There's some challenges around that, not least of which is skills transfer. If people who know how to do things now if their skills are still needed in 70 years' time, how do we make sure that we capture and maintain those skills? That's a real challenge. Doing it faster would, of course, help solve that problem. The other things that we're looking at doing on this is, yes, some of the other parts of the task. So this is a glove box, chemistry lab version. It's a fairly standard piece of equipment for handling dangerous objects, dangerous chemicals. There will be some in this university site. You put your hands through those gloves and operate the task. You're now operating through, it's basically 2, 3, 4 millimeters thick nitrile rubber, butyl rubber. It's a thick, chunky thing. It makes it hard to hold something. It makes it hard to feel something. Currently, nobody does what I would have thought was obvious, which is to embed sensing in the gloves so that you can feel what's going on better. That just hasn't happened yet. Is that something that can be done with tactile sensing technologies? Probably. Is it worth doing? That's another question, because we don't have enough understanding of what we can do with tactile sensing to see how it could be used on a piece of hardware like this to make that task better. We can imagine how we would use robots with a task like this, but actually it might be more interesting just to use the technology as a way to enable this. So what we're looking at doing is fairly obvious, really. Put a pair of robot hands, put it in a glove box, put it through the glove box ports, use that to do the task. We know we can do really capable dexterous tasks like that. This is the prototype of a system that later turned into a robot kitchen, doing the same task that a chef does to make a meal. What we did to do that was to have the chef teleoperate the robot to do the cooking, and we recorded it and played it back, because it turns out that, of course, once the robot has done it once, if you put everything in the right place, it's easy to do it again and again. And that didn't even need tactile sensing or autonomy or vision, machine learning, nothing. It was just a simple teach and repeat system. Of course, what that can't do is cope with variability. If the bowl of tomatoes is 1 millimeter too far to the left, the robot won't pick it up. You have no tomato in the soup. To get robots to do useful tasks, we can start by saying, let's have a human show them how to do it, but we then have to capture the sensor data from those robots and work out how to use that to encapsulate the skills that the humans actually did and to cope with variability. So, oh yeah, this is another nice demo. We don't think anyone had ever tried playing catch with a robot like this before. It's not a great game of catch. It's somewhat dull, except for the fact that we hadn't done this. What's interesting there is the lag in controlling the robot is somewhat noticeable, but because the sense of touch is very immediate, it's possible for the person to actually get the capture to work right. And we've done this over quite long distances. We've had a sense of touch working across from San Francisco to London over the internet, and we had 160 milliseconds latency on the touch feedback and about half a second latency on the video feedback. And what was interesting there was video latency is a real problem if you can't see what's going on. So if you can't feel what's going on, but as soon as you have a sense of touch, video latency stops being a problem because you can feel that something has happened. So sorry, commercial plug, we are now selling this kind of robot hardware. In this shot here, I'll just explain, Mike is not wearing a VR headset. Mike is wearing a blindfold. As he moves his hand across, when the thumb touches the ball, he feels that, and that's how he can close and grasp it. So this is now something that we think is, we're at a point where we can start to build really interesting, useful, dexterous telerobots, taking the sense of touch and working out how to exploit that, how to use that, how to do interesting things with it. What I want to do now is to find out what we can do with that we couldn't do before. What's effectively the new possible. So, that's me. Keep it fairly brief, short and simple. Any questions?
Thank you very much.